Everybody, or almost afternoon probably. My name's Colin King. I work partially for Zero. As Simon said, we were really where I do their risk management from a point of view of moisture and energy use. But my background really comes from spending many decades working for the BRE as their head of hygrothermal risk, which is heat and moisture, and building defects. So really for the last, I can't really remember how many decades, but basically I've been involved in government work on Part L, C and F of the building regulations, where I sit on the steering group. I sit on the BSi committee 5250, Management of Moisture in Buildings, which is the code of practice for all buildings in managing moisture. It used to be called condensation, but moisture risk is much wider than just condensation, and that's sort of some of the stuff that we'll go through today. I chair CB 401, which is the BSi committee on new energy efficient standards, and then sit on the various other committees like the Ofgem Technical Risk Panel, where I turned down most of their innovation as being crazy, and other government sort of bodies and advisory things. But it's really about understanding the causation of moisture and the effects of damp and mould, which is really where I want to focus where we are today. So I'm going to take you on a bit of a journey really about understanding damp and mould, why it's there, what it is and what it does and what it doesn't do. Mainly because the fact it seems to be one of the hot topics at the moment because of energy costs and the risks that people are actually running at the moment by not being able to heat their properties to an adequate level. And what's adequate? Well, that's dictated by building physics. So we'll touch a little bit on that. Um, and then really the fact that I've been doing some work on fuel poverty at the moment for government, where we're now looking at about 45% of the population going into the winter with fuel debt, is that they actually haven't cleared their financial debt from last year because of the cost of energy, even with the support that government gave me, which is quite worrying. Because if once we get into that colder end of the year and energy costs, which are unlikely to come down significantly, are still at that level, we're really going to have a big upturn in complaints if you're working in social housing, but also in your own homes on damp and mould if we can't afford to adequately heat all of the property. And then if you're in the rented sector, of course, you've got the whole Awab's law going through after that young chap that unfortunately died to exposure to extensive toxic mould, and his the complaints, all the rest of it were to a great extent ignored. And a lot of housing associations have the default that if there's a moisture or a damp problem, then it's actually the resident behaviour. So we're actually going to go into that a little bit today as to how much do people contribute towards the issue of damp and mould. You might be interested that the World Health Organization put out a report last year which said damp and mould, it's not the people, which was actually a big watershed really, because a lot of the time it was put down to inappropriate behaviour. But actually when you look at the numbers, it's very rarely just down to that. It's a lot of other things which cause those issues. But anyway, I won't go on because I can talk about this for hours. I'll try and keep it to an hour. But basically we're just really looking at the issues around mould and damp. I don't like the term damp because it doesn't really explain the whole issues, because damp is a term for many things, whether it's old damp in older buildings, which is historic, it's been there for a long time because of the inherent structure of the building, or whether it's falling damp because of leaking gutters, whether it's rising damp because of a failed DPC, or whether it's penetrating damp because the wall isn't maintained, or whether it's internal damp because of high levels of relative humidity within a building. So what we're really talking about in a building is moisture balance. That balance between heating, ventilation, and moisture creation, to get that balance absolutely right so that we end up with a good internal environment in terms of indoor air quality and reducing the risk of mold, which is fairly difficult to do at times. But basically, the bottom line is mold is not good for anybody. Even if you're in the peak of fitness of health, mold can have effects on you and has some significant effects. It can cause headaches, nosebleeds, all sorts of different things when you can actually get mold toxicity syndrome, where you actually become allergic to the presence of any molds. So it's about controlling those molds which are prejudicial to our health, and there's about 6 of those. There's also several hundred molds which are really good for us. So all mold is not bad, but there are certain people, groups of people, that are more susceptible: babies, children, elderly women, elderly people, pregnant people, those with a predisposition to eczema and asthma, or a weakened immune system. Um, and what has been proven is that long-term exposure in children can cause asthma. Before, there was no ever medical link between mold and actually causing asthma, but that link has now actually been proven that in young people it can actually cause asthma to occur. And a lot of it is about the amount of mold we are exposed to, how close we are to the mold, uh, and this all affects how sick we get. So, as in the case of Wab, it was in a bedroom where the toxic mold was really extensive. It was within 600 millimeters, 900 millimeters of his activities nearly all the time, and he spent a lot of time in the bedroom. So it obviously became a critical situation. And the longer you're exposed to it, the issues become chronic. And there's an evidence suggestion at the moment that UCL and others in the academic world are looking at that exposure to mold can cause depression, which was especially relevant in lockdown, because there were people who weren't getting out, they weren't allowed to mix, they were staying in properties that were perhaps not ideal, that we're now starting to reap the perhaps the mental issues that people have had by being in lockdown in non-ideal situations. So it's not something to actually be ignored to any great extent. And the new law coming out by a government will put in very, very quick turnaround times for properties where the residents report mold. One of the other bits of work I'm doing at the moment is on the housing health and safety rating system, for what that might look like from a legislation point of view. And what happens is that the toxin from the mold build up in our bodies, and then cause things like insomnia, brain fog, anxiety, depression. What they're trying to prove at the moment is a causal pathway. At the moment, it's all fairly anecdotal rather than evidence based. But when you start plotting the data, it's quite obvious that there is some sort of link, but we need to prove it. And if you look at the recent Good Home inquiry, it found that 4 million homes in Britain were found to be non-decent with the presence of mould. When you look at it, we've got about 26 million homes, and we know of about 4 million of those which are non-decent. So it's about upgrading those, and part of that tool was really the update recent to Part F of the building regulations, ventilation indoor air quality, which now looks at a completely different process of dealing with indoor air quality, makes a requirement for a ventilation and indoor air quality strategy, which has never been there before. So the wheels of government are turning slowly as ever, but certainly turning in the right direction of how do we get on top of this issue of damp and mould. And this is some of the work we've been doing at the UKCMB, Centre for Moisture in Buildings, and it's looking at where are all these issues and what is the evidence process for that. And what we've got is that when you look at dampness and mould, it is the area where nearly all of these symptoms are found to be exacerbated. And what we're looking at is that at the moment is the quality of the evidence. And all the ones in the peach sort of colour are actually where there is good evidence of an associated risk from damp and mould to those things. So when you look at it, rhinitis, coughing, wheezing, respiratory, asthma, dyspnea, hypersensitivity, bronchitis, all of these things which are down to how we breathe are more likely to be exacerbated when you're in a house that's got dampness and mould. And what you also find is that over the last 10 years, we've had a massive upsurge in house dust mites and bed bugs. And this again is linked to the levels of relative humidity in a building causing the exact right environmental conditions for them to actually breed. And there was something like an 86% increase in the presence of bed bugs and dust mites in people's properties. So it's important that we get this evidence base, because what we don't want to do is actually sort of jump in with a sledgehammer to crack a nut, but actually it needs to be an appropriate response to these issues, because all of these issues do put pressure on the NHS and what actually happens. And when you look at it from the building regulation point of view, you look at the standard that Part F of the building regulation wants to achieve, whether it's new build or retrofit. What we're looking for is this optimum relative humidity, where most of these things don't want to actually exist. And this optimum level is about 40 to 60% relative humidity. And we use the measurement of relative humidity because it's a metrics that people actually understand. In the building regulations, it also talks about absolute humidity and active water. But most people more relate to levels of relative humidity because it's something that's easier to measure. When we get round to actually having smarter homes with intelligent energy systems and in-house monitoring, we will actually be in a better position to ensure that we achieve these correct levels of relative humidity, actually start looking at VOCs and other things which actually affect indoor air quality, because that's really what Part F is trying to deliver, is good indoor air quality. But you can see that this band where we're at our healthiest, if it's too dry, it's not healthy for us. If it's too moist, it's not healthy for us. It's this zone where we as humans actually perform the best. And then it actually reduces the risk of doing this. And that's where the issues kick in, when people perhaps don't live as appropriately as they should. They turn off ventilation systems, they block up vents, they don't use or don't have undercuts on the door. And it's about understanding the importance of the ventilation system in this whole conundrum of reducing the health risks associated with damp and mould. So yes, the people do have a part to play with it, but it's not really as big as perhaps we've in the past thought it as. So it's about delivering this conundrum and jigsaw of moisture balance. And when you look at a building, you really have to think about moisture in all its forms. You're looking at moisture as a solid, when it's ice, when it's a liquid, as in water, or whether it's a gas, as in water vapor. And they're all important because ice can affect the performance of the fabric of the building through freeze-thaw frost damage, where the bricks become saturated, they get frozen on very cold days, and it destroys the fabric of the building. When you think of the building actually having a primary function of protecting its inhabitants. And then we have liquid mortar, which is really, when you're looking at liquid water, we're looking at things like falling damp, timely maintenance, actually maintaining the properties, cleaning the gutters, making sure all the seals around the windows and things like that, all the penetrations from services and that, don't allow water to actually get into the building. And then we deal with the moisture as a gas, water vapor, because that's where we get that internal relative humidity right to put this building into that moisture balance. So we're ensuring that the fabric of the building is resilient to the passage of moisture. That's part C of the building regulations, contamination and moisture. And then it's liquid water, which is about RMI and timely maintenance of the building to make sure that the water is allowed to get off the building as quickly as possible. That's the function of the roof and the drainage and the rainwater goods, is to allow the water to get away from the building as quickly as possible. And then we can look at how do we deal with this internal water vapor to make sure that it doesn't get to a situation where we have saturated vapor pressure, where moisture gets pushed into the fabric of the building and causes interstitial condensation or surface condensation if it's allowed to get out of hand. So it really is this conundrum of considering water in all its forms, because all of them pose a risk to this balance of moisture risk and balance inside the building. So really what we're looking at from this moisture context point of view is the systems, the ventilation system, whether it's background or mechanical. We're looking at the fabric to make sure that the fabric is resistant to the passage of moisture, that it is watertight, that it does the function. The context is that we actually have enough money to heat our properties and maintain our properties. And then the fourth part of this moisture balance is activity, people, because people actually generate a lot of water vapor every single day, even if they live in a appropriate way. If they start to do things like drying clothes on radiators, which heaven forbid none of us ever do, or actually not opening the windows when we have a bath or a shower, which, why would you do that in the middle of winter? You know, there's all of these things that have to rely on proper background and purge ventilation to make sure that this activity doesn't become the tipping point to push us into high levels of relative humidity, where we will end up running the risk of mold and damp and all those associated risks. And that moisture balance now is something that building regulations part F requires you to do. BS 5250, the management of moisture, also makes you look at this moisture balance. Whereas before in the British standard, it gave you prescriptive solutions. What it does now is it makes some design solutions and then sets out the principle of how you're going to deal with this moisture balance in the building. And it's important because if any one of these four things becomes broken, then damp and mold is inevitable. It's that four pillars that if either of these are out of sync, something will go wrong. If the fabric is not watertight, water will get in. It will actually end up with cold water surfaces that will probably be closer to dew point, which means that even relatively low levels of relative humidity will still hit dew point at that interface with the cold temperature. If the activity is wrong, as in the house is overpopulated or used inappropriately, that then undermines that pillar. If you haven't got enough money to heat the building to a reasonable temperature, the NHS indicates a reasonable temperature at being 18 degrees. If you look at most of the buildings which are actually suffering from mold and damp, their average temperature is about 13.5 to 14.5 degrees. It means that mold and damp is almost inevitable. And then if you look from a systems point of view, if the ventilation is either not suitable, not operational, not maintained, not delivering its design ventilation rate, then again, it runs the risk of the excess moisture not being allowed to get out of the building. So it's important that we all understand that this moisture balance, especially when we're going forward, when we're looking at our focus at the moment is on decarbonisation and net zero, and everybody talks about energy reduction and energy use and decarbonisation of that energy. I don't hear many people talking about indoor air quality, about how we deal with this moisture balance, which is difficult, more difficult in airtight buildings, especially when you look at, we don't always get the quality of installations of MVR, say MVHR systems that we would actually like. When we looked at Part F 2 years ago, went out and tested a lot of buildings, be it passive house or new build or even retrofit, over 90% of the systems that were put in were not meeting their design ventilation rates, or they had been installed incorrectly, that things like insulated ductwork was actually just a flexible pipe, that there were dead ends, that there were condensate traps, that there was even some circumstances where I went out where the blanking caps had still been left on the MVHR when they were commissioned, so they weren't working at all. So it's about making sure that if we have these systems, they are commissioned and recommissioned seasonally to deliver the required rate. The new rates in Part F, and I would recommend that you actually look at new Part F, because the ventilation rates are far higher than they've ever been before. And about 30% of the ventilation systems that were on the market when we did it didn't meet that requirement for quantities of ventilation. They're all updating it, but it does make a requirement that you assess the whole principle of the house, undercuts, background ventilation and mechanical ventilation is actually appropriate, which is more than it's ever been before. And if you look at relative humidity and its reliance on temperature, air temperature, you can see that if you had a building with a given moisture load and that was only heated up to 10 degrees centigrade, that building would be at 100% relative humidity. The air would not be able to suspend any more vapor within its structure, so it would be looking for cold surfaces to deposit that water onto. Old historic walls, glass, metal surfaces, any type of hard surface. To lift the temperature of that building to 20 degrees, which is where building regs does that design, that 20 to 21 in the living room, 18 degrees everywhere else, that's the design set point temperatures. The relative humidity comes down to 52%, which is exactly the zone that we need to be in to make sure that all those other things are less likely to happen. And then if, whatever reason, you had the temperature up at 30 degrees, which I would never really suggest anybody should, the relative humidity goes down to 28%. But that's why in the Middle East and the Arabian countries and other warmer climates, they don't have issues with mold and damp like we do, because the air temperature is always relatively higher. Theirs comes because of the air conditioning and those other issues that come in. So it's important that when you look at temperature, design temperatures for people in houses, that 18 to 20 degrees is not really open for debate. That's where people need to be able to heat their properties, which is why we do things like insulation, draft proofing, other simple measures to make those buildings more cost effective to heat. Because obviously if you reduce the amount of heat loss, you end up being able to heat the building more cheaply, which means that people that are in fuel poverty are more likely to be able to create an environment where the relative humidity is between 50 and 60%, which is where we ideally want them to be, but then taking into account the context of whether they have any disabilities or mobility issues or their age or predisposition to conditions. It's a complex issue to maintain that, given the fact of how people move and live and actually how the building performs. So if you look at people, you're looking at a family of 4 producing over 20 pints of water vapor in a day. And that's if they live normally, just existing. This is not about drying the clothes on the radiator. This is not about blocking vents. This is what happens normally. And you can see that one of the biggest issues is people breathing. If they breathe, it's 4 pints of moist water vapor a day. So, and that's without using their home as a gym or doing other things, which in lockdown was actually happening. So what we were actually finding was that when a family was actually locked down in the buildings that we were actually monitoring, that figure of 20 pints a day actually went up to nearer 30 pints a day. And then we had issues about the fact that people couldn't actually heat the building properly. So we ended up with these ongoing issues. But then when you actually look at that, on top of that, we've got to think about plants. We've got to think about wind-driven rain, where moisture and vapor is actually forced into the building. You've got the construction moisture, which is old damp. Our older buildings are damp because they've been around for 150, 200 years or more. They were built of lime and more natural materials, so they are inherently damper than more modern cementitious construction buildings. There is the issue of rising damp because of a lack of maintenance or others, and then inadequate ventilation. So even in the ideal world, we're still having to deal as a design issue with over 20 pints of vapor in a family of 4. Now, if there's other things like they're ambulant disabled or they smoke, all of those sorts of things start to increase. This is just sort of Mr. and Mrs. Average, really, is that 20 pint figure. But it's a lot of moisture that you either have to heat the building appropriately, so the bulk of it is suspended in the air. You look at those extreme events, so it's actually ventilated properly, but also the building's kept in a good condition so that the structure can actually deal with it, so that we don't get things like interstitial condensation and all the associated risk of those with dry rot and wet rot and things like that by moisture being forced into the fabric of the building. And if you ever really get involved in designing buildings, a lot of the time you'll find that this is just dumped on the M&E package. I will get them to sort the ventilation out. But it rarely comes with a proper ventilation strategy for the design, occupancy, and potential use of that building, so that moisture as we go forward doesn't become an issue. And it's really, really important. Always easier with new build because you're starting with a blank canvas. But if you look at most of the buildings which exist, they all have these issues: rising damp, penetrating damp, falling damp, lack of maintenance, over occupation, all of these things which make them more problematic to deal with, especially now our focus is on decarbonisation and energy reduction. But we're doing all of the insulation measures, we're doing all of the technologies, but we're only just starting to think about, well, we need a ventilation strategy at the same time. And PAS 2035, which I helped to write, has its own section, Appendix C, which is all about the ventilation strategy for that building, because you can't do one without the other. If you're only focused on energy reduction, you will get moisture issues. If you only focus on moisture issues, you won't get the energy reduction. So it is this whole systemic balance of the building in the approaches that we actually take. So I always like to think of damp and mold as a bit of a jigsaw. And actually, how do we get all these bits to actually work together so that we've got heating? The occupant must be able to heat the habitable homes. So basically, we've got those rooms, they've got to have a system which is capable of raising the temperature up to, as I say, a minimum of 18 degrees in a reasonably good time. They've got to be able to afford it, which is one of the challenges when we go forward to coming off gas and moving on to heat pumps. Do they understand how to use them? Can they get that quality of heat? Are they capable of delivering that heat in all of the locations? Maintaining our buildings for all of those issues which allow moisture to get into the building. The ventilation has to be right. And if you look at new Part F, you'll find that just putting in 2 intermediate extract fans is not enough. It doesn't deliver the ventilation, whole house ventilation rates required. You need to be thinking about DMEV at the very minimum as a ventilation system, and minimum 9mm undercuts and trickle vents in every window. That way then you are capable of getting somewhere close to the requirement for background ventilation. And then if the building is a complex geometry structure, as in it's used to be a single terrace house, but now there's an annex and then there's another extension, it requires other ventilation cores to be put into all these other rooms, because the more complex a building gets, the more complex it is to ventilate it properly. And historically, if you look at damp and mould, kitchens and bathrooms which have ventilation are very rarely the locations that damp and mould is formed. It's in circulation spaces and underheated, underused rooms of the house. So most houses you will go into, we've all got one, I've got one, the back bedroom on the north facing wall, which I dump all my stuff in. I very rarely heat it very high, and so it suffers from mold. That's building physics. It gets no solar gain. It has no occupation. It's underheated. Damp is inevitable. I've been doing this stuff for 30, 40 years, but I have a room with mold in it. I know why it's there, but it's something that I have to manage. So we are all sort of the victims of our own, or we're the authors of our own demise, because we know we do things that aren't quite right, and that, oh, I'll get round to, I'll do that another time. I'll do that mañana. I've got better things to do. But that's the reality of it, is you run that risk with mold. And then you've got the occupant behaviour about drying clothes, cooking, showering. You know, I went through a situation where I had 3 teenage boys. We had excessive moisture creation when they all decided to shower. Apart from the fact that they were in there for half an hour, an hour and a half of moisture creation with it going through the roof, which then unfortunately was exacerbated by the quantity of links that 3 teenage boys can spray over their body. If you want problems with indoor air quality, have 3 teenage boys and not a very big house. And that's the thing that you have to challenge with, is these are normal. You can't say they won't happen, they're not likely to happen. They do, and they happen in every single home across the UK and wider area. So it's about this jigsaw. Think of all these parts that feed into the solution of damp and mold. Heat it properly, maintain it properly, get the people to live in a more appropriate way with education and help, and then ventilate it properly. And then we'll have some hope of getting out of some of the issues that we actually have. So then if you look at indoor air quality, what happens if the CO2 levels, concentration of parts per million, gets higher and higher as you go on through lack of ventilation or lack of consideration of things that go on in the building? So 250 to 350, that's normal. 350 to 1,000, so concentration is typical of occupied indoor spaces, but it's got reasonable ventilation. The fact that the windows open, the doors open, people use the room. As soon as it goes over 1,000, what you then start to move into is this sick buildings, where actually people start to get drowsy. The air quality is actually poor. Once you move on to 2,000 and above, it's headache, sleepiness, stagnant, stale, stuffy air, poor concentration, loss of attention. It's a lot of, if you go into a meeting in an old building, if you actually measure the parts per million of CO2, you'll find it's not uncommon in small meeting rooms for that parts per million of CO2 to be up around the 4,000 mark, which is why people find it difficult to concentrate in those meetings. And even in in schools, in some of the older schools, the real issue of air quality in schools is a real issue, and something Ireland's doing a lot of great work on bringing in standards for indoor air quality in Irish schools, which we've yet to embrace. And then you've got 5,000, which is actually the legal limit for workplace exposure. But it's okay having a legal limit, but how many places do you actually work in where they measure CO2? I've never been in one, unless you actually go into a laboratory environment where they have CO2 monitors. Well, we measure carbon monoxide because it can poison us fairly quickly, but we don't worry about CO2, where it can have a detrimental effect over us on a long period of time. The effect is exactly the same. The event is not quite as extreme. So what we know is we've got the benefits of good ventilation, about understanding all of these things, that if we can control this, the mold spores, the mycotoxins, CO2 odors, the particulates, the volatile organic compounds from furniture and fittings, that we build these new houses, we put all these lovely fittings in there, but they are leaking VOCs because of the glues and the bondings and the resin that are actually inside that structure as they're put in. And yet we hand them over and we've got people living in them straight away. And yet all of these things are going on there, and then we have to make sure that they get to the right temperature, humidity, CO2. It's that whole sick building syndrome that we perhaps don't consider as well as we should when we're designing new buildings, when we're occupying new buildings, or even when we're actually having a change of use in buildings. That actually the system may have been designed for A, but now we're using C. So we worry about the layout, we worry about the lighting, but do we actually worry about the indoor air quality? And a lot of the time what we do is we use the building regulations as the end point, whereas actually building regulations are a minimum standard, not a maximum standard. All our designs and considerations should start at compliance with the building regulations and move forward. To get to building regulations is like, yeah, you've done the least you had to. It's a starting point, not an end game.
Colin, on just thinking about what we were talking about earlier on, was there when it comes to moisture balance, does like traditional convection heating or is better or worse than radiant heating? I mean, does it matter what type, how you heat your house? Whether
very much so. If you look at a house that's heated by gas, it gives off water vapor. Yes, and it's probably cooking more because we have balanced flues and stuff like that. But there still is a high degree of water vapor given off by the heating. So yeah, the type of heating is for moisture balance actually critical. And what you have to, and the problem that you always have is a lot of the heating systems, which are probably some of the better ones. Like I'm a real as I said earlier, I'm a real fan of infrared heating. It gets absolutely crucified in SAP because it's treated like an ordinary electric panel heater that's only 100% efficient, which they're not. They're more efficient than that. And they work in a completely different way because they're not about heating up the ambient air temperature. It's about heating the structure up, the things which have mass. So yeah, and obviously the worst thing you can do, which unfortunately is what a lot of people in fuel poverty do, is that they actually heat their homes with portable gas heaters. If you've got a Cala gas heater and you use that as your main heating in a single room, each one of those puts out a gallon of vapor in the contents of its gas canister. So you find that, and I see it a lot when I do disrepair claims and sort of legal situations like that, is the people are in fuel poverty. They've bought a portable gas heater. They're living in one room, so the rest of the house isn't heated. They use this heater because they can spend £20–30 on a gas. It's a known quantity. It doesn't give them a bill. They live in this one room. The relative humidity in that room goes absolutely through the roof. Then they open the living room door, and all of this, when you think about the weather, the high pressure to low pressure, relative humidity is exactly the same. High vapor pressure caused by this excessive activity or heating the fuel, the liquid gas, and then all that vapor migrates and it finds itself a cold surface, and that's when the spores start to settle. But within 12 hours, those spores will start to germinate, that will then start to generate hyphen, and all this happens before the mold becomes visible. But that accumulative moisture that always happens is in that one room, lots of, or everybody goes in one room because it's easier to heat one room. All of that vapor from breathing and living and activity then comes out of that open door and it migrates up the building. High pressure to low pressure will always go upstairs, go into the bedrooms where we spend vast quantities of our time, which is where the mold then grows. But you don't see it straight away because mold can grow within 12 hours of the ideal conditions. And then it starts to become visible after 7 days. And then at the period of about 28 to 30 days, that's when it then blooms and you get this visual appearance of the mold there. You know, I've seen some fairly ridiculous claims by people saying that they've got a system that can indicate when mold's going to grow 7 months before it happens. You know, it's a complete load of toss. Once you get those ideal conditions, mold can grow within 7 hours, 12 hours, and will be visible within a week. And then you've got to worry about, well, what type of mold is it? Because there are lots of different ones. So when you look at these mold growth, it's all that the conditions are, it's the ideal temperature to grow, the ideal relative humidity, the type of substrate, and that's the presence of nutrients, food for the mold to grow. It's a living organism. It needs food. And unfortunately, houses which are dirty are more likely to be moldy, because if you've got a dog and it comes in and it shakes and God knows what it's been rolling in when it's been outside in the mud and the water, all of that ends up on the wall. All of that is nutrients for mold to grow. And then the pH of the wall, and the pH is important because when somebody sends in Mr. Damp Check, all he does is he changes the pH of the wall, which lasts for about 7 to 10 days and the mold dies. But the root cause has not been identified, so within 7 to 10 days, it's back again. You know, actually changing the pH of a wall with a damp wash or a mold wash is a completely pointless exercise unless you actually identify the root cause of why that mold was growing in the first place. It's like painting the fourth bridge. You'll be back there, you know, within 7–10 days constantly. And it needs light. It doesn't need lots of light, which is why it likes growing behind cupboards and wardrobes. You know, that everybody's got it. You move your wardrobe, oh God, there's mold behind it, because the air doesn't move, the temperature is different, and it creates the ideal environment for mold to grow. And it needs oxygen, and then it needs time of exposure to all of those favorable conditions. But what you find is people go, oh yeah, well, you have to get to 100% relative humidity or very high levels of relative humidity for mold to grow. It's not true. Mold grows at 65% relative humidity. And what you've got is all of these different xerophilic types of mold, which rely on different levels of relative humidity. The one that probably most people are familiar is Strachybotrytis, the black mold, the toxic mold. That one needs something in excess of sort of 80% relative humidity, which is why the building regs don't want you to ever allow the relative humidity in the building to go over 80%, because that's when Strachybotrytis kicks in. But you've got all these others, Aspergillus, Penicillium, all of these other molds which will grow at lower levels of relative humidity and are just as toxic. They're not as visible, but they're definitely as toxic and cause other issues if if sort of ignored. But it's these conditions is what allows mold to grow that you have to break. And it's a difficult conversation with somebody in their house if you tell them the mold's there because it's dirty, because you don't wash your walls, because you don't clean your house properly. But in some circumstances, that's exactly the truth. But they don't want to hear it.
Yeah, Colin, we have a number of questions coming in, and I'm conscious
sure.
we've only got 10 minutes left. So Pablo was asking, he said he'd like to know, what about the positioning of the insulation and its relation to condensation? There's a general understanding that having internal insulation is risky in terms of condensation.
Yeah, absolutely. Internal wall insulation is technically the most challenging to get right. Mainly because of the fact that it puts the structure, which may have historic moisture in it, on the cold side of the wall. So you're more likely when you have internal wall insulation to run the risk of interstitial condensation, because what you've got is that cold interface of the new insulation and the old existing structure. And what you also find when you do internal wall insulation is it's very difficult to deal with the thermal bridging. Whether you're actually looking at intermediate floor level or the connection of the wall to the roof or the wall to the floor, you've then got to reach this internal critical temperature factor of 0.75. Otherwise, you run the risk of actually getting condensation and mold on adjacent surfaces. You don't get condensation and mold at the thermal bridge because that accelerated heat loss reduces the risk of condensation and mold. But on the adjacent structures, there's a higher risk, which is why you have to reach this FRSI of 0.75, which is it's a thermal bridging value. It shows that the U value temperature difference between two elements is not more than 75% out of sync. So internal wall insulation is really, really challenging. And if you do partial insulation, like leave the kitchens and bathrooms in place, then it's destined to fail.
Right, because then Ruth follows on from that by asking what types of installation are effective in the management then. And she's asking about like real world as opposed to what the data sheets say.
Yeah, well, with that, what you actually need is a coherent strategy of how you want that building to perform. So if you look at more modern buildings, they are of cementitious material that resist the passage of moisture because they're strong, because they are consistent. So basically, they work by keeping the water out. So if you have a more modern building and your building is vapor closed, then the insulation needs to be vapor closed. So you have a coherent strategy of moisture movement across the structure. So conversely, if you've got a building that was built before 1920, 1930, which was originally vapor open, it would be clay bricks or natural stone of a lime-based mortar. It would have had a lime-based internal finish, be it lard and plaster or even just lime plaster. But the coherence of that structure is that it allows moisture to move from outside to in and inside to out. If you then put in a vapor closed material on the internal face, you're actually disturbing that coherent strategy for that wall. So if it's a vapor open wall, then the insulation has to be vapor open, and it has to be vapor open from outside to in. And if it's vapor closed, then it's vapor closed from outside to in. Otherwise, you have an incoherent strategy which is destined to fail. So what you're looking at is things like vapor open material, like Pavatex, Pavadenso, some of these insulated lime plasters, which allow the free flow of water in the form of vapor through the structure in both directions. Because what you're trying to do is actually mimic the original vapor strategy for that structure, even though they didn't think about it in those times. They used the materials they had. But what happens, you have vapor diffusion, surface diffusion, capillary conduction. You need to make sure that that wall is kept in equilibrium of how it's dealt with in terms of moisture movement for the last 200, 300 years since it was built. But if it's more modern, built of concrete, cement, the idea is you keep the water out And so therefore the insulation internally can be, if you put a vapor open on the inside, it would be incoherent, and you'd end up with a higher risk of interstitial condensation because the material is wrong for that structure. So you would use, I don't know, an EPS and XPS. You've obviously got to manage the new issues around fire risk and stuff like that, but mineral stuff like that. It's stuff which is not necessarily hygroscopic.
Okay, because then Tony's actually sent me a direct message as opposed to everyone, and he's asking about sprayed cork insulation applied on the internal face of external walls.
Yeah, and cork insulation is okay, but it's not okay if you then put a gypsum plasterboard over the top of it and plaster it, because then you've got a non-vapor open finish to a vapor open material. It's not coherent. So if you're going to use cork, what you need is a vapor open plaster finish to actually deliver that coherent structure.
Okay, thank you. Everyone's come out of the plasterboard woodwork, so to speak. Got multiple questions here. David, he's saying, regarding old buildings, can you elaborate on the contribution to raised levels of damp and condensation due to, for example, the wrong paint, wrong mortar, wrong plaster, use of cement, inject DPCs?
Absolutely. When you look at buildings that were constructed probably prior to, I don't know, 1920 is an arbitrary date, they didn't have DPCs. They don't need a DPC. They've never needed a DPC. Why would you inject a wall with some mythical snake oil or unicorn oil into a structure where the wall is about 18 inches, 24 inches thick, and you've got this liquid that supposedly gives you a continuous barrier across the whole of this structure, which is random stone and random brick and full of voids and everything? It's just no. You just don't need it. What you need to do is, when you're looking at diagnosing rising damp, it very rarely ever is rising damp. What you usually find is it's lateral penetrating damp caused by ground levels outside or internal finished floor levels, which are destroying the equilibrium of the structure. And then through capillarity, the moisture is being pushed up the structure, because the older parts of the structure, the smaller the hole, the higher that water will raise up a structure, which is why clay bricks and lime mortar, which has got very small voids in it, through capillarity, allows moisture to rise up. It's diagnosed as rising damp. It's not rising damp. It's the fact that the water pressure is too high at the base of the wall of the structure. It's only ever rising damp if you have the presence of hygroscopic salts. And even if you do a calcium carbide test, all that does is measure absolute moisture. It doesn't tell you about hygroscopic moisture and hygroscopic salts. So the only way you can do that is you would have to do a calcium carbide testing, and then the sample would have to be oven baked to find out what of it is hygroscopic salts and damage from hygroscopic salt moisture, and how much of it is actually rising. And 9 times out of 10, you'll find that it's not the presence of hygroscopic salts. It's actually the fact the wall has got too much pressure, because the soft landscaping is up against the outside of the building. The water pressure, when it rains, it stores the water at the base of the wall. The wall acts like a sponge, pulls it up. Take the pressure away, put a drainage channel on the outside of the building. Mysteriously, the rising damp problem goes away, and it doesn't cost you £3,000 for a whole dose of unicorn oil in your wall. So, and it's exactly the same with mortar. If you've got a lime mortar which is vapor open, it's got very high levels of porosity, and it's very soft. If you then put cement over the top of it, the cement is too hard, and then what you get is micro movements at the interface of the lime and the cement, and water gets behind it. So the water gets behind the cementitious material. The background moves more than the outside does, so it becomes a rigid fascia on that wall. The water gets behind it, it's then isolated from wind drying and solar gain. It falls, it fails. The pointing comes off, and somebody comes along, oh, I'll do that for you. I'll give you a nice strong new pointing of it. Whereas what you actually need to do is rake it out to a reasonable depth and reproduce it in a lime that is suitable for the substrate. If you put modern materials into an older building, it's just not a coherent strategy. This building was designed to allow water, vapor, to move from outside to in. In the old days, what we had was an open fire that took all the excess moisture and threw it up the chimney. We don't have those internal environments anymore. So we think that putting something that's really strong on the outside of the building will keep the water out. It won't. It will bypass that and cause issues somewhere else.
Right. Okay. John's asked, does Colin agree with the content of Pete Ward's book, The Warm, Dry Home?
So what does...
Have you heard of the book, The Warm, Dry Home?
Yes.
Yes, I thought you would do.
Yeah.
Colin, John is asking if you agree with the content within that book.
I think a lot of it, yeah. I don't think if you ever get any two people that are classified as being knowledgeable about a subject will agree about everything, but there's a lot of common ground. Yeah. I think that what you have to do, and what I would do, the book is a good book, and it comes from a sound position. What you have to do is understand that it has to be taken in the context of the building that they're standing in front.
Mm-hmm.
I don't find that you can ever have one strategy that fits everything. It has to be taken into the workmanship, the materials, the age, the maintenance, and the context of that building. And then you apply those principles, but you can't always apply them in a broad brush. You take the ones which are relevant to the context of that building.
Okay. Okay. Two things actually. There's two more questions, but we've hit the hour mark. What I might ask you to do offline is see whether you'd be prepared to do another session, because obviously it has generated a lot of interest. Before we end, Alex has asked if brick creams work or are they snake oil?
They can work. I've actually used them. I've used Storm Dry, which is a brick cream, and I used it on a listed building. So yes, they do, and they do act like a bit like Gore-Tex for buildings. The issue with them really is, how do you ensure that the application is homogeneous, that everything is covered? Because what you don't want to do is actually leave any weak spots for it. The main issue with the brick creams, especially with the work that I've done on Storm Dry, and I did a lot of testing on some of the snake oil versions of these materials, and I actually did which I'll send you the link to, I did a report with UCL on the efficacy of brick creams and wall treatments, which government actually published, which we went into it and did a lot of laboratory testing on how does it affect the porosity, does it allow the building to still breathe, does it do what it says on the tin? And to be honest, the only one that came out close to what they claimed was the Storm Dry system. But the main thing is, when you put these brick creams in, the clay bricks that you apply them to are not really the issue. The issue is the lime, because lime is very porous, clay bricks not so much, and the moisture content difference, when you've got a clay brick, it's quite normal for it to have 6% moisture content by volume and it still be dry. But if you look at lime mortar, the normal zone for that, it can be 12-13% moisture content by volume because of the different types of structure. But brick creams, yes, they can, but they're not a forever solution. There's something that you have to go back to. I think the manufacturers talked about 10 years. When we run the cycles in this report that I'll send you the link to, it looked like 5 years was a more realistic lifespan for this treatment, which is a lot of cost, because a lot of these buildings, when they're maintained, they have a one-off shot at doing something. And there's very, very rarely enough revenue to keep going back every 4 or 5 years to do it. It's like a painting program. It doesn't really exist to any great extent. So yes, they do, but it's a buyer beware. Make sure that the application is good. Make sure it's consistent, and that actually there's a strategy to replace it in 3 or 5 years when it will naturally have eroded.
Okay, thank you. And then lastly, Stuart's asked, he said, he's looking for a tool or a device that allows him or anyone to measure and monitor indoor air quality. So you can start taking some real-time data.
Yeah.
Do you have any suggestions or recommendations?
Yeah, there's lots actually out there. There's a company called AmbiSense that's doing lots of good work on indoor sensors. AMBI Sense. They're doing a lot of work. We're actually a company that I do a bit of part-time work with at Zero. We have our own B, which is a building energy monitoring system, and there's quite a lot of them out there at the moment, where they actually monitor VOCs, particulates, relative humidity, temperature, and IES. It's a bit like the SMETA data, the report that came out from UK government a while ago about SMETAs, smart energy meters, and it's really taken that to its next evolution, which is looking at relative humidity, temperature, and other things. And if you've got other people out there that are doing it as well, there's a few companies that are now offering this as we can help you maintain your indoor relative and humidity and temperature. The trouble is that they rely on having one RH logger, and the location is always put in, which is convenient for the electricity meter, not for the area of the building which has the highest level of risk of relative humidity, which is why I like the AmbiSense system, because what it does is it gives you small sensors which can then send it back to the management system from various locations. And if you understand the type of building and where the high risk is, because it's not that difficult to understand the buildings that are most at risk, that you can put the sensors in there and it can give you a real-time warning. And what it can do is it can measure things like internal moisture load by measuring active water. It also does relative humidity because that's relatively simple, and you can see whether it's a transient moisture load or whether it's a permanent one, which active water would be. And then it can look at temperature. You can see whether the people are playing their part in being able to heat the property up to a reasonable level. You can use CO2 as a as a proxy for occupancy. We know how much CO2 people give off. So if there's a high CO2 load, it may give an indication of over occupancy, therefore over occupancy, over moisture load. But yeah, I can dig a few out and send you the links if you want
to. That'd be kind. Thank you. Yeah, we can add those to the notes on the recording. No, thanks, Colin. I'll follow up with you after this once we've gone offline. But no, thanks for taking us through what I imagine was only part of your presentation. But we'll and lots of good questions there. So I'll follow up with you afterwards. But thanks for everyone else for joining, asking the questions. Hope you found it extremely useful. It looks like you have done. Appreciate you joining the call. And thank you very much once again, Colin. And
I'm more than happy to pick whatever topic subject you actually want. I've got quite a wide range of experience in dealing with older buildings and strategies and moisture and stuff like that. So anytime. I'm more than happy.
Fantastic. No, I'll ping you offline. Brilliant. Thanks, then, guys. Have a good afternoon.
Okay.
Speak
Thanks,
soon.
everyone. Thanks for coming. Thank you.
Bye.